grateful for hosting us, and Brian. This is an awesome venue. So before I introduce the speaker, I also would like to thank Adam and EA for sponsoring Tianqi's trip to LA. So let's thank EA. And Adam is going to tell us a few words about EA.
So just a show of hands, how many of you guys have played an EA game? Alright, this is my kind of crowd. Alright, so if you play EA games and you like video games, we're hiring data scientists at all levels. We have multiple offices around the globe, and we also encourage people who like to travel. So we have offices in LA, we have San Francisco, Seattle, Texas. If you like to stay in LA, we have a couple hundred people here, good data science team. We're part of the larger global analytics team, so we work cross-functionally across the globe, and we work on all of the games across EA, console, mobile. We're primarily focused on the top titles, Madden, Star Wars, FIFA, etc. And we love people who have experience with XGBoost, deep learning, people who like to use machine learning in production, as we do, or people are really excited about using machine learning to encourage players to have good experiences in the game and personalize how they interact with the game, sending players the right message at the right time, giving them help as they go through the fatui if they're having trouble drifting around corners. We can use machine learning to identify the right way to recommend, hey, remember to press A at this time, things like that. So we're also using it for things like smarter AI, for dynamic push notifications on your mobile phones, and all sorts of new types of applications we're exploring. We're doing a lot of exciting things over at EA. Feel free to check out our careers webpage, careers.ea.com, or reach out to me. My email is ahusein, or Adam Hussein, at ea.com. Thanks.
All right, thank you. So, how many of you have used XGBoost before? How many of you have competed in a Kaggle competition? All right, pretty good. So for the rest of you who have, how many have you heard of XGBoost before the quiz talk? So even more people. So for those of you who are not very familiar, so XGBoost is one of the most awesome open source machine learning library. It implements gradient boosted machines, which is one of the best, most performing algorithm for supervised learning on many data sets. I use it daily for work, and we are very lucky to have here Tianqi Chen, who is the main author of XGBoost, and who has also received many awards. For example, the John Chambers Award for XGBoost, and also the High Energy Physics meets Machine Learning Award from CERN in Geneva. He's still a PhD student, amazingly, but I think his software beats many of the software that has been done by companies that have put dozens of people working for years. So we're really lucky to have here Tianqi and talk about XGBoost. So let's welcome Tianqi.
So okay, let's get started. Today I'm going to talk about XGBoost, scalable tree boosting system. And here's the basic outline. So first I'm going to talk about what is the machine learning model behind. So what is the basic idea, and what can we do to derive all the algorithms in this type of machine learning algorithm. Then I will talk about a bit more about what kind of features we have in XGBoost that can help us to make data science and make machine learning useful in the production. Finally, I will conclude talk with some use cases of real-world impact of XGBoost. So to get started, if you think about machine learning is now everywhere in many of our productions when you talk about data. And however you think about machine learning algorithms, actually there are not too many type of machine learning algorithms that are actually used in production, I would say. There are a few type of machine learning algorithms that are particularly useful. And for example, if you think about large-scale advertising system or other kind of click-through rate prediction system, you will need a good logic regression or large-scale linear software to solve these type of models. If you think about recommender systems, there's a type of model called factorization model that you want to build all the users' items and maps them into a latent space, and you can use it to do a recommendation. And nowadays, you have heard about this deep learning trend. They can recognize their images and generate audios and do all those magical things that you heard about. And deep learning is yet another type of machine learning algorithm that can be used in production. And today, the major theme of the talk is about tree-based algorithms, actually. So tree-based algorithm is this type of algorithm that's invented in the 90s that are actually not very well recognized. I would say there aren't too many papers about tree-based algorithm recently in academic, but it's still very, very useful in the sense that you can find it in almost all production systems of machine learning. The reason is that tree-based algorithm actually works very well for tabular data. By tabular data, I mean everything that you can pull out from a relational database. And that almost means anything that you can, almost all the things that relate to your production. So as a few examples, you can find that this tree-based data can work on anomaly detection that detects anomaly events. And for example, with high-energy physicists use tree-based models to detect potential events in large hydrogen collider so that they can discover novel physics. And it's also used in the click-through prediction or fraud detection to detect fraud. It can also be used to estimate risk or in finance or insurance. So yes, there are a lot of use cases of these tree-based models using tabular data. So what is a tree-based model? I think many of you already heard about decision trees. So today we're going to talk about a bit variant of decision trees that's called classification regression tree. So in here, this is what typical tree-based model looks like in a commercial system. So assume that you want to do a recommendation to see if this person likes computer game or not. So you can recommend product EA to the person, given by the demographic information of the users. So what a tree-based model basically does is that it establishes a few rules to categorize each of the user into each of the categories. And on each of the leaf node, actually, there's a prediction score that basically associates with how likely this group of people is going to like computer games or not. So this simple model have a few interesting perspectives. First of all, you can find that actually it can learn the hybrid of multiple conditions so that it can combine features like age and the gender together. So that you can save you a lot of effort of doing feature engineering in a sense that it can automatically combine some of the features together for you. So usually, if you do tree-based models, a single decision tree, in this type of tree is called regression tree. A single regression tree wasn't enough for solving all the problems. So what people usually resort to is this type of model called tree ensembles. So in tree ensemble, actually, you will have multiple trees to make a prediction. So here we have sum of two trees. And to make a prediction of a certain user, what you will do is that you will use the first tree and the second tree to generate two predictions and sum the two predictions together to get your final likelihood score. And this type of model is what model actually generates many of the data of our results in many of the application domains. And there are many ways to learn this type of tree ensemble. For example, one common way is called random forest, which randomly generate independent trees and aggregate them together. Today we are going to talk about different type of algorithm called gradient boosting. That is more powerful in the sense that they will try to learn the trees in a non-independent way. So every iteration, the algorithm will try to add a new tree such that the second tree can complement what the first tree does not learn well. So in a sense that gradient boosting is a more powerful way to learn those tree ensemble models. Okay. So there are a lot of algorithms to learn tree ensembles. Here are a few of them. Actually, most of the algorithms you can find that these algorithms are invented in the 90s. And actually, all the algorithms that I mentioned in the beginning, like recent hype of deep learning and neural networks, also come from 90s. So So if you want to find something that's useful, it's likely that it have been already invited like this. The difference is that we have more data, and we need more powerful tools to fully utilize all this information to get us a good prediction. So what XGBoost does is actually sits on a variant of original version of gradient boosting machine that try to incorporate additional regularization term, which I will explain later. And it really helps us to get a better prediction in many cases. So there are challenges and advantages for using tree-based models. I've mentioned a few already, actually, in the first part of the talk. Tree-based models are usually highly accurate because they can combine all those evidence together. And it's very easy to use compared to other models like linear model or neural network, in the sense that it's invariant to the input scale. So usually if you use other type of models, you need to rescale your input in some nice way so that they don't blow up your training. In tree-based models, it's highly likely that you can directly take your data from a database and throw that into a model and will work out of the box. So it also is easy to interpret in the sense that you can use various tools to inspect what's going on in a learning model. However, there are still a few challenges in a tree-based model. In a sense, the first challenge is that because this model is so powerful, we still need ways to control overfit. In a sense that we can generalize our prediction well on a test set. The second challenge is that we are getting more and more data, so we really need to build scalable solutions to solve this type of averages. So what is XGBoost? In short, so I've listed a list of features about what XGBoost is, but in short, it's just a powerful system that does one thing very well, in a sense that it's a much faster tool to learning better models. So first of all, in this part of the talk, what I will do is I will tell you what does XGBoost learn, in a sense that to elaborate on what is the better model, what's the better model part mean. Then I will elaborate a bit more on what XGBoost can do for you, in a sense of how it can scalably train all your possible data and the other features that may of interest in doing data science. Okay. So this part of the talk will contain a bit of more mathematical derivations. However, I will only assume basic level of calculus, so hopefully we can follow derivations. I will pause a bit on the crucial part, but trust me, if you pay a bit careful attention, you should be able to derive the general gradient boosting algorithm from scratch. And I think this is a worthwhile thing to do, so that you can all understand what's going on in behind. Okay. So machine learning 101. So there are several elements of supervised machine learning that you need to care about. These are all the key concepts that they want to care about. The first key concept is about model. So a model means that given your input data, say the age, gender, or demographic information of users, how you can make predictions given this information. For example, a very simple model you can use is a linear regression model that basically take a linear combination of all those features and generate your prediction. A second thing about this type of thing is about parameters in the model. So in the linear models, what you will have is you will have a set of vectors that represents the weights you will associate to age, gender, or each of the features. Finally, there's one important thing that helps you to learn those models given the data set you have. This is called objective function. What objective function does is that given a training model, it measures how good the parameter is, so that what you will do is that in the searching algorithm, you will search for the best parameter that fits the objective function. And if you think about objective function, it usually contains of two parts. The first part is about training loss. That's easy to understand. If you want to fit a linear model, it's more likely you want your prediction to be very close, at least on the training data, to be very close on the already provided label. Training loss basically measures how well you can do on the data set you have on your hand. The second term, which is usually actually ignored by many of the beginners of machine learning, is called regularization term. In the sense that it's not enough to only fit well on your training data, because eventually you want to make predictions on your data that you haven't already seen. So you want to be careful to regularize the model such that this model is simple enough, so that you can make reasonable future generations. We'll have more examples on this later. So if we put the tree ensemble learning to this context, we can find that it maps nicely into the concept of supervised learning. So if you think about tree ensemble learning, the model of the tree ensemble is actually a class of regression trees. So say we want an ensemble of k trees. It's a class of k functions, but don't be afraid about the function space. It's just some notations about k decision trees we're imagining. And the objective function we use exactly follows the general supervised learning principle in the sense that we can define a training objective function that measures how well we do on the training data. It can be arbitrary objective function, which means that you can, usually if you look up from the existing literature, you can find objective functions for learning to rank, that how to rank your input according to user preferences. There are objective functions for doing regression to give you a good prediction score. There are objective functions for doing classification or predicting the click-through rate of a user, of whether a user will click through your data. And more importantly, there's a second term about regularization that measures the complexity of a tree. So in a split, it means that you want to encourage trees that are simple. Okay. And here again, you can find that I keep emphasizing this kind of formula about the objective function that containing the training loss and the regularization. So in a nutshell, if you want to optimize training loss, what you want to do is that you want this model to be predictive. So it can be more, you can predict your training data set accurately. But if you want to optimize it for regularization, it actually means that you want to encourage simple models. And the simple model is quite important if you want to generalize well in a feature data set. So we can do that by a simple exercise of fitting a one-dimensional decision tree visually. So here is our data set that contains all those data points here. This is a one-dimensional data set. Say this is a data set of the interest of the user over some product over time. So in each year you will get each one of these data points. I want to fit some kind of like regression tree on this data set. If you think about one-dimensional decision trees, actually it corresponds to a step function. Because what you do is you split on the time and you will assign a real number to each of the steps. And we have several candidates of step function here that you can fit to this data set. And that illustrates the bias variance trade-off or the training loss and the regularization trade-off perfectly. So on this case, actually, you can find that you can fit a very complicated step function to this data point. And actually, this step function fits most of the data point quite well, which means that they have very low training loss. But it's a quite complicated model, so it has a very high model complexity. On this graph, actually, it's a quite simple model that's a two-step function. However, it does not fit the data points very well, so it has a bit higher training loss, but a low model complexity. And this model is actually visually best, I will argue, in a sense that it gives you the simplest form to fit all the data points perfectly. So hopefully you are now convinced that it's quite important to trade off both the training loss and the regularization objective. In order to do that, actually what we need to do is that we want to define the complexity of a decision tree or regression tree, because we are actually trying to fit tree ensembles on a data set. So given a regression tree, we are breaking it into two parts so that we can make our definition more formal. The first part is called the Q function that represents the structure of the tree. So Q function basically maps each of the instance to the leaf index. So Q of the boy actually is 1, means this leaf index 1. And Q of the grandma is 3, which means that if you it maps the grandma to the leaf index 3. And given each of the leaf index, we also have a W vector that corresponds to the weight of each of the leaf. So this tree structure can be formally decoupled into the structure of the tree and the weight you assign to each of the leaf. To define the complexity of the tree, we use this definition. Actually, there can be multiple definitions, but this is a definition that we find that's quite helpful. So the definition says that the complexity of the tree is linearly correspond to the number of leaves in the tree. So if you have more leaves in your tree, it's going to be more complicated. It's also There's also a penalty term on the L2 norm of the leaves, so that it will encourage leaves that have smaller weights. In a sense that if you have smaller weights, the prediction is less likely to be affected by small changes in those positions. So intuitively, this is the formula that we can use to measure the complexity of the tree. So given the complexity formula of the tree models, you can plug in arbitrary loss functions that you care about and combine together to learn your model. So how can we learn the tree ensembles? So now we have those objective functions that contains the training objective and the regularization term. The problem is that what we need to learn is the structure of a tree as well as the parameters in the leaf. So it is not possible to use traditional methods like stochastic gradient descent or Cohen descent or those methods that you can learn from a traditional textbook. So what we can do instead is called additive training. And I think usually additive training is where the boosting comes from, because boosting basically equivalent to additive training. So what you will do is that you will start from scratch with no tree at all. And every time you want to try to add a new tree to your model. And when you add a new tree to your model, you will keep original trees, keep the original function unchanged. And through this step, we are improving our model by adding a new tree again and again over time. The only problem is that how do we select which trees or which functions that we can add at each of the run? And the answer is we always want to add a function such that it will optimally help us to decrease the objective function that we define actually. So here's a bit where a bit math kicks in, but it will require a bit. I think this step is okay. So basically, this is by definition. You want to add so you want to optimize your training loss plus a regularization. And the second thing what it says is that you want to this prediction of t run equals the prediction of t minus 1 run plus this new function that you add to here. And we want to find a function, or we want to find a tree that minimizes these objectives. If you put it into a simple context, for example, a typical context of regression trees that is a regression scenario, where you basically have a square loss that measures how different your prediction is from your label. In a regression scenario, this quickly becomes a quadratic function, which is quite nice. And this term is usually called residual term, that measures like the difference between the label and the current prediction. However, it's not possible to have this nice form in general objective functions. So what we can do instead is that we can take a second order Taylor expansion to do our approximation. And this is the most tricky part of this slide. So by definition, any continuous function can be approximated by linear combination of this first order gradient and the quadratic function of this second order gradient. This is called Taylor expansion in your calculus course. And if you trust this expansion, what you can do is you can define a first order and second order gradient over the objective function. And this original objective function can be approximated by a quadratic function that can be expressed by the second order and the first order and second order gradient. And if you put it into a context of square loss, if you're not comfortable with Taylor expansion, then you can find that if you plug square laws back, you get exactly what you have in this slide. So this function, which is exact. So yes, for square laws it's not approximation, but for general laws it's an approximation. But it's okay to have approximation in a sense that we are doing multiple steps, and eventually we can prove that it will converge. Okay. Another nice thing about this protocol is that you can find, for any object functions, your sufficient statistics to define this approximation function is only the first order and the second order gradient. This will provide a very nice feature in a sense that XGBoost allows you to optimize for arbitrary object functions that you can calculate gradient and second order gradient for. And we have interfaces that allow users to plug in their own definition of gradient and second order gradient so that you can optimize for objective function that you care about that may not be predefined in the system. So, given our new goal, what we want is that we want to find the function that optimizes this new objective, this quadratic function. Okay. Here comes the interesting part. So what we can do is that we can regroup this objective function by their counterpart in each of the leaves. So basically what we'll do is that we'll plug in the definition of a regression tree back to this quadratic function. So here is just f of t is defined by w, which is the leaf weight vector, if you recall. And q is the mapping to map x to their corresponding index. And in this step, what we'll do is that we'll do a grouping. Instead, we will group all the instance. We'll group index by the index that will categorize to node 1 and the index that will goes to node 2. And this sum basically becomes this sum in a sense that in I of j here is a set of index that classifies q of x into j. So in a sense that it will regroup this formula, and you will find that it's actually a sum of t independent quadratic functions, and t is the number of leaves. Okay. So now we have a sum of t independent quadratic functions, and what we want is actually, we want to ask that what is the optimal weight we can put into so that we can fit the tree best. To do that, what you can do is that actually you can take the quadratic function and you can take a gradient and calculate the minimum of the quadratic function, which is by definition is this one, and you can plug that back to the original objective function. So you can find that actually we can find, given an existing tree structure, you can find an easy scoring function to score this objective. So this scoring function basically measures how good a tree structure is given a fixed tree structure. And for this fixed structure, we can also have a formula to get you the optimal leaf weights. Okay. I know this may sound a bit confusing, so let's look at the more illustrative view of how you can calculate these objective functions. Basically, what you have is that on each of the instance, you have your gradient statistics, and the second order gradient statistics associated with each of the instance. And what you want to do is that, given an existing tree structure, you can classify each of the node into the tree structure, and you have an index set of big I of j that gives the set of index that will be classified into this. And all you need to do is that you want to calculate some statistics of gradient and second order gradient of the instance that's classified into that node. And using the gradient statistics and the second order gradient statistics, you can use this objective function we derived to measure how good this tree structure is. So if you're still not very comfortable about this, think about what you will do to measure a quality of a decision tree. So normally what you will do is that you will basically classify all these nodes into each of the nodes, into each of the leaves. Then you will measure like how pure each of the leaf score is. That's called Gini index. And what we derived here is actually a more generalized version of Gini index, in the sense that this structure score basically measures how good we can improve the objective function that we define. And depending on what kind of objective function you choose, this structure score basically reflects how well you can improve against that structure score for an approximate way. So this is basically a more generalized version of impurity measure of decision tree that helps you to guide your tree learning to tailor towards this regularized objective function. And if you like to do a derivation again afterwards, you can go to the XGBoost documents. We have a detailed model explanation file that walks through the derivations. Okay. So what we have is that we actually, given the tree structure, we have a scoring function that scores how well this tree structure is. So now all we need to do is we want to search over all the possible tree structures and get best tree structure you can have and add that to the ensemble and do that again. So this is like a brute force enumerations that wouldn't actually happen in practice because there are infinite amount of possible tree structures here. In a sense that if you consider continuous split over any axis, there can be arbitrary number of continuous split on any of the data points. So what people usually do instead is that we will grow a tree greedy. In a sense that every time we'll start from a tree without anything, and you will add splits to the branches recursively. And every time, what we'll do is that the structure scoring function is still our friend. In a sense that we can use the structure scoring function to measure how good what is the structure score before you add a split, minus the structure score after you add a split. And that is the structural that is the gain that you can have by adding that split to your tree. And you can show that it's given by this simple formula. Basically, this formula says that the gain you can have with the score that you can get on the left side, the score you can get on the right side, and the score you can get if you don't split at all. There are several interesting things about this formula. For example, you can find that there's a complexity penalty here. This means that if your gain of your structure score is less than the gamma factor, it's better that you do not grow this leaf at all. And that leads to the pruning strategy actually, and that's where the regularization effect kicks in a sense that we always want to encourage trees in a sense that every split kind of contributes a significant amount of structure scores, so that if there's not too much gains, we'd rather just prune off. And usually pruning is not implemented must implement in the tree boosting systems. XGBoost is one of the systems that implements the pruning strategy for this generalized regularization functions. So that if you use a default setting, usually you can get a very good performance because of pruning. And why is regularization better? You already see the example of visually fitting the step functions. And hopefully you are convinced that we really need a good control strategy so that if you want to generalize your examples to more data points, you will want to have a good regularization factor. And another interesting thing here is that usually if you talk about decision tree and pruning is usually is discussed as the heuristics, like you want to do prune if your loss getting smaller than something. What we do here instead, we derive this formula from the supervised learning principle. So that you can understand what is the exact objective they are optimizing for, and you are optimizing for that objective. So you know that what you are learning for. Okay. So given this structure score, what we need to do is actually do an enumeration to enumerate all the possible splitting points. To do that efficiently, what you can do is that, say we want to enumerate what's the age split of all the instances is. And basically, it can be any of the age split between these persons. So this graph basically illustrates what you can do to optimize for this kind of enumerations of arbitrary splitting points. What you will do is that you will sort all the data points around the features that you're interested in. And all you need to do is basically calculate the sufficient statistics of gradient, the second order gradient. So all you need to do is actually just do a linear scan from the left side to the right side to enumerate over all the possible splitting points. And this is a strategy that usually used in the tree-based algorithms. XGBoost offers a bit more optimizations on this strategy, but this is a general idea of what you can do and what you can learn from these models. Okay. So I've finished the introduction of what does XGBoost learn. Hopefully you are now convinced that it's quite important to do regularizations and add more formal regularization to the tree-based models. And the takeaway message is that XGBoost try to optimize the regularized objective so that it gives you better generalization accuracy, which means that not only it fits well on your training data, given new unseen data, it can potentially give you better prediction performance. And we give a generic additive derivations of any objective function so that you can use it to optimize for problems like ranking, classification, and other things. And the structure score functions can be used to search over structures. And this is quite generic in a sense that this principle can be used to solve problems not only for binary trees, but other tree structures. If you are ever interested in other type of tree structure, that can help you incorporate your problem. I need to mention that the derivation here is not like original in a sense that it's a contemporary derivation of what the Friedman does in the original GBM paper. But one important thing here is that we introduce this more generic rigorous objectives and this more cleaner derivation so that everybody can understand what's going on. And the regulations helps you to control your model complexity. Okay. And the final question is that why do you want to take all the pains to deriving the algorithms? It's actually quite interesting in the sense that it helps you to understand the algorithm better. And it also helps you to build the software better. For example, because we know that by derivation, there's isolations between objective functions with the sufficient statistical gradient. So that in the software, you can isolate the objective function part from the tree boosting part. So you can use the same framework for any type of objective function that you can define as long as you can calculate gradient. And this is one of the things that you can do by deriving things more formally. Okay. So let's go to the second part. What can XGBoost do for you? First, I want to show two code snippets for. So there are a lot of things that XGBoost can do for you, but I think one of the most important thing that features that why people use XGBoost is because it's fast. In the sense that it's very well optimized. Try to push the limit of your resources to try to do the gradient tree boosting algorithm for you. And actually, that's why the name XGBoost comes from, because it's called extreme gradient boosting. In a sense, it's a system goal that want to push all the resources to do the gradient boosting for you. And you will see later how does it come from. There are also other nice features that we'll go through that can be quite helpful when you do data science analysis. So this is what you can do in Python. Basically, XGBoost program looks like this. So you can load your data into a data structure called D matrix. You can also ingest from any Python data structure like data frame, pandas, or like NumPy arrays. Then you call training function with some magic knobs that you want to tune. And after you train the model, you can run a prediction function. This is what it looks like in R. So basically, it's very similar. You load the data, you do fit the model, and you run a prediction. And actually, you can use XGBoost in many languages, including Python, R, Julia, and I think Scalable, Java. So, and all these implementations shares a common core implementation in C++. So that you can train your model in one language, load it back in another, and so that if you ever work together in some like testing and production environment, you can use the same implementation over all the time. Okay. One of the interesting features of XGBoost offers is the automatic handling of missing values. So actually, if you're ever working with real data set, you can find that missing value is everywhere. There's always some missing value. Either it's user did not provide the value or for other reasons. Usually in traditional machine learning, what people do is that people ask you to impute missing values. Like you want to, if the age is missing, you want to say you want the impute age to be average age of all the users. Instead, what XGBoost does for you is that XGBoost introduces missing directions. The missing direction is a special direction that the data point will go if that provided value is missing. Actually, if you think carefully, you can find that this missing direction approach corresponds to learning an optimal imputation directions. In the sense that if you enforce the default direction in some way, it will correspond to the imputed value on that specific branch that you end up with. More importantly, during the learning process, actually, XGBoost will automatically learn what is the best missing direction you should go at each of the branch. instead of asking users to provide what is the best missing direction that you need to do. How do we learn it? Actually, we use the same structural scoring function, except that we search the different choices of missing directions. So that's another example of the formal derivation can help on this step. So if you ever use XGBoost and you have missing value in your data, you don't need to do anything and just specify what is the missing value. It could be 9, it could be other, like -999 or whatever. And it will automatically figure out what's the best way to impute these missing values. And it usually works better than manually imputed approach. There are also very nice features about interactive feature analysis, in a sense that you can build your model and you can look into what's going on. Here, what we do is that we can look at what's going on in each of the trees. You can do it in R, you can do it in Python. And if you ever use other languages, if it's not available, you can save the model and you can do it in R and Python by loading back. So this can be very helpful if you want to look at the insights of what's going on in the models. And there are other type of feature visualization analysis. For example, this is an important analysis that analyzes how important each of features that contributes to the data set. Actually, the interactive visualization package of our package of XGBoost is contributed by a lawyer. His name is Michael from France. And what he used XGBoost. He needed the feature because he wanted to use this interactive feature analysis to catch what is the common pattern of people doing tax fraud. And what he do is he will apply this XGBoost to this tax fraud data, and he will use feature important analysis to see what are the common features that people use. So you can find that this type of models can really give you insights by not only give you very fast training, which I will mention later, but also gives you insights on what you learn in the model. Another thing that XGBoost does quite well is that XGBoost is very well optimized for sparse data. Usually, tree-based models are not very good at sparse data, I would say, but sometimes there are some sparse data due to various reasons. For example, if you have categorical data, or in statistics people call it factor data, then usually people do a one-hot encoding, and you end up with a matrix with a lot of with a lot of entries that's a 0, and only a few of them are 1. Usually, a traditional tree-based algorithm will need special treatment for this type of data, or basically they just ignore the fact that people will come up with this kind of format and not handle it quite gracefully. So what XGBoost does instead is that XGBoost internally, the implementation is sparse aware in a sense that it can handle sparse data natively. So that if a user end up do feature engineering that contains sparse data, it will just do very well. In a sense that, for example, this is the comparison between whether you use sparse data, sparse aware approach, or not use sparse aware approach. You can find many magnitude of difference. And the difference not only in computation cost, it's also in the storage as well. Okay. Yes. So one of the important things that we consider when we design the framework is that we want it to be quite extendable and flexible for the user. As one of the example, what you can do in XGBoost, you can use your favorite language, whether it's Python or R or Java or Scalable, to define the customized objective function. So in case that the objective function that XGBoost provides natively does not fit your need, you can design your own objective functions and plug it back to XGBoost and it will work natively. Not all framework does this, in a sense that if you think about many frameworks, what they do is that they act as a black box. Instead, what XGBoost tries to do is XGBoost tries to open as much as possible to the user. If you have some expertise in the things, you can directly hack into the code, and actually that gives you much better productivity. So the library itself is actually very modular. There's a plugin system that allows you to directly plug in, for example, customized data readers that can directly load your database into XGBoost data format. You can also plug in other things. Because this kind of modular design, it allows you to have even more extensions. For example, recently there's a pull request on the new variant of tree boosting called dropout for tree boosting that's adopting some tricks from neural nets back to tree boosting. And it's a work in progress that have been pushed back. And actually, because of modular design, actually it's only like 300 lines of code that we use all the existing tree building and other modules of XGBoost. The code is also designed to be very portable, in a sense that the entire library has literally no dependencies. There are two submodules that we designed so that if you basically you can compile all the libraries in a single C++ file. This means that you can ship the library directly to your mobile devices with no problem. And you can do other funny things like what we did for our another library called the MXNet. You can basically compile the library into JavaScript and run the system on the browser. I haven't tried that, but I can show you it's possible. Okay. Another interesting example about the extendabilities is this kind of early stopping API. So this is not an original design feature of XGBoost. So what this feature does is that it allows you to take a validation set. So usually when you do gradient boosting training, you will need to decide how many number of trees you need. And you need to decide, like, for example, whether I need 1,000 trees or 100 trees is enough. So what this API does is that it will design for you. Basically, what it says is that you can provide the early stopping run, and you will continue running until the validation area does not decrease. So this is a very interesting feature that allows many of the calculars for doing machine learning competitions doing quite well in all those competitions. And this is a feature actually contributed by the user of XGBoost. Why are they able to contribute this type of features? Actually, one important reason is that because all the entire training loop of XGBoost is exposed in the native language, so that you can write all those logics in Python or R, in a sense that you can use your own knowledge to hack into the model, so that there are other features like continuous training. You can use different strategies on different iterations. And recently we have a new callback API that allows you to plug in any callbacks between those iterations. So you can, for example, save your model every iteration and do other interesting things. And this wouldn't be possible if the method is not tightly connected with the native API. Of course, the most important thing about XGBoost is being able to train very fast. In a sense that I would say it's almost the fastest implementation of the tree boosting algorithm that's available, and we throw all the possible optimizations into the thing to make it quite fast. Okay, and this is the benchmark from Shiad on the. I think he did a very interesting thing in a sense that gives us the common ground of comparing all those things. So there's a competition, and there's also encouragement of all the tools to move forward and to make the tools better for our users. Okay. And what we take away from this comparison is actually we can find that, first of all, XGBoost does very well over all the possible data set size. Secondly, actually, usually not all the tools do very well on a small data retrieve because it's hard to parallelize things on a small data retrieve. But sometimes you still need to do repeated experiment on a scale like, it's not small data, I would call it medium data, like million level or like 100,000 level. And XGBoost actually runs more than 10 times faster than all those existing implementations in those regions. How does it scale to larger data retrieve? There are several key solutions in XGBoost that haven't yet done in any of the existing solutions. For example, one thing that we do is out-of-core computing. It means that you don't need to store all your data into your memory. Although that nowadays we already have a very big memory, so you can likely train like 10 million data points or 100 million data points in a single machine without a problem. What if you cannot? Actually, we provide a solution to store the data into your SSD or external memory storage. And we use external memory computation to several techniques to improve this external memory computation. In the sense that we are adding compression, sharding, and other system optimizations. So that in the end, we can train this is 2 billion data points on a single machine. without problem. And that 2 billion data points correspond to around, I would say, around 1 terabytes of data, uncompressed. XGBoost also works very well on distributed setting, in a sense that we have a very flexible and portable implementation that can port to various platforms, including Hadoop, and also other popular data flow programs. If you ever care about scaling your tree boosting everything to data to a scale of billion level or even beyond billion level. But if you only care about 10 million or 100 million, you can just use a single machine version. That will work perfectly. So in the distributed settings, you can find, again, this is a log scale plot. So a difference actually means a lot different. So on the left side is the end-to-end cost of building 10 trees, including loading the data from the distributed file system. This is an AWS environment, so we are loading from S3. On the right side is the per iteration cost, excludes the data loading cost. So one to take home message here is that actually it's not only magnitude faster than the existing implementations, it also scales to larger data sets by using the external memory computation and all the resources. That means that you can basically use fewer resources to train train models with larger data set. And that's what we mean by pushing all the limits of the resources you can have in the machine. We want to fully utilize the memory, CPU, and the SSD and hard disk that you can get in your system. As a combination, you can find that XGBoost gives you a very compelling solutions on this kind of distributed setting. Okay. So I've talked a lot about what XGBoost can do for you. Now we want to talk about what XGBoost cannot do for you. And actually, this is also quite important. In the sense that in the beginning, when I built these machine learning tools, we kind of have a very ambitious goal in the sense that we want to solve everything for the user. However, actually, that's not the best approach, in my opinion, to build this software. In the sense that we always have a limited energy, so that if you want to solve all the problems, you end up solving none of them very well. So XGBoost does not solve problems like feature engineering, hyperparameter tuning, and I can enumerate even more cases in that scenario. What XGBoost does instead is that XGBoost tries to integrate it very well with the existing ecosystem. For example, in the Python side, you can directly take data, you can directly do feature engineering using pandas or all the existing data frame pipeline. In the R, you can use the data frame to do feature processing and use the same backend to do the XGBoost training. If you want to do hyperparameter searching, XGBoost is natively integrated with the existing ecosystem like scikit-learn API, so that you can directly use all the features in scikit-learn to do hyperparameter search and all the other pipeline engineering features, but replace XGBoost to do your gradient boosting tree training. And you can do that same thing in the R as well. And this is quite important in the sense that this is one piece of thing that works very well, and you can put it anywhere that you need it. And because it works very well with the existing ecosystem, you can take fully advantage of all the existing power of open source system and build your data science solution in a very, very good manner. So I would call it the Unix philosophy of machine learning, in the sense that it's exactly a unique philosophy, in the sense that we want to build one thing that works very well, and we want to make it compatible with as much things as possible, so that you can port it to any other platform. It can run in any of the things, and it can make use of any of the existing ecosystems that you have. As one big example, this is one example of this kind of unique philosophy in a distributed manner. So I've talked about distributed XGBoost. Actually, usually when people talk about distributed machine learning, sometimes you will see that you will need a specific environment, like you want to run on Spark, or you want to run on MPI, or you want to run on other environment. The distributed experiment I did on the previous slide actually runs on Yarn natively, which means that on any of the existing commodities cluster system, they have a cluster scheduler like Yarn. You can directly run XGBoost. But we also want more things in the sense that if you consider nowadays what does the what does the machine learning stack looks like? It looks like this. You have some platform A that does some feature engineering job, like Spark. You have another platform B, like there's an alternative to Spark. For example, Flink is another alternative to Spark. And there are other things like Google have its own cloud data flow. That's another cloud backend that does all those data flow jobs for you. On each of the platforms, actually, they have their own customized implementations of each piece of machine learning software, which is kind of tedious in the sense that you need one piece of machine learning software in almost all replicates of all these things. What we want to do instead is we want to provide a unified piece that you can use in any of the environment that you have. So, as an example, what we build is that we have an XGBoost on data flow pipeline that builds the integrates XGBoost natively into a JVM stack, so that this framework can run natively on top of Flink and Spark. And actually, the framework is quite portable in the sense that you can even port it to any of the cloud data flow that you can find in the existing cloud market. What it means is that the machine learning algorithms, the cloud platform is no longer restricted by the machine learning algorithm, in the sense that we have a unified algorithm that allows you to use whatever cloud platform you use and whatever training system you use. And it does not solve more problems like feature engineering and other things, but it solves one problem very well, and you can use that everywhere. Okay, so I've talked about what does XGBoost learn and what XGBoost can do for you. Finally, I want to talk about a few slides about the impact of XGBoost. So, it has been used by most of the large companies. I wasn't able to say what the specific use case is, but it's indeed used in the big company's product pipeline. And I also have some quotes from users. For example, it's used in the WeChat recommendation platform which is the Chinese version of WhatsApp, that tries to use the user features and do recommendations. Because XGBoost is designed to be very portable, so that it can directly port XGBoost into our internal production system without problem. And this is quite important in the sense that it also helps you, because the library is so lightweight, in the sense that it doesn't create too much burden to use this in any of our production pipeline. And it's also used by many of the machine learning challenge winners, in the sense that if you look at the Kaggle competition, which is a popular platform for doing machine learning challenge over the last year, you can find that more than half of the machine learning challenges actually winning solutions use XGBoost as a part of winning solution. The second most popular method is actually deep learning, which I think used by 10 solutions in the past. And it's also used extensively in the common machine learning competitions like KDE Cup. So one important thing that I want to highlight is that this is a very active open source community. So we get a lot of active contributions back from the user itself. So that user is the one who really knows what's really unique. So for example, the early stopping API that really helps a lot of Kagglers to get their best model available. And the interactive feature visualization API really helps Michael and other colleagues to gain insights into the model there. So by having a healthy community, we actually can grow in a sense that but focused on that specific problem of building really boosting better for everybody. So I want to pause a bit and talk about broader context in the sense that XGBoost is a part of an open source organization we call DMOC, which is an organization that created by me and a few other PhD students doing large-scale machine learning. It's an organization hosting open source projects with a goal to make high-quality machine learning, large-scale machine learning software available to a wider community so that research results can be quickly adopted by many users. XGBoost is one of the examples of doing tree learning very well and try to push our limit to do the tree learning quite well. We have another example called MaxNet that tries to aim for the domain of deep learning. So MaxNet is this library that that we built for deep learning that resembles similar idea of XGBoost. It's very similar to TensorFlow, but in a sense that it's more lightweight. In a sense that you can port it to many of the existing devices and fully utilize all the resources you can have on the node. For example, we have a JavaScript binding. If you go to the website, you can find a JavaScript binding that directly run the image classification on a browser, on your own browser, and it can be ported to mobile devices and any other operation system. We also have the most wide range of interface support. For example, this is the only library so far that support deep learning in R language. Okay. So going back, I would encourage every one of you to take a look at the DMOC XGBoost page and contribute back. Because one of the most important thing and amazing thing of open source community is that users always help to drive a project, and by combining all the efforts of users together, actually we can benefit from each other and really build a software that's quite high quality. And I think that's one of the reasons why XGBoost is successful. It's because the successful XGBoost actually comes from all the efforts from more than 100 contributors that contributed to the software. And what you can do is that you can not only contribute code, you can create tutorials. If you have any great use case of XGBoost, there's a resource page that you can contribute to so that others can see about your use case. And there are already a lot of tutorials, videos about how you can tune parameters, how you can use this on the different learning scenarios, how you can use this to win Kaggle competitions or other machine learning competitions. And this is a great start, and if you are interested in contributing to this, and I'm sure that there will be more exciting incoming things in XGBoost in the future. So I would like to thank all my collaborators, including the major committers of XGBoost, and the other users of XGBoost community. And with that, I will be very happy to take questions. Thank you.
Thank you so much. This was awesome. So we're ready for our questions.
You talked about the data normalization, or that's a big part of it, right?
You mean data normalization?
Or how much normalization or data wrangling do you have to do to put into this?
Okay. First of all, like I said, data normalization, data wrangling is part of feature engineering. That's one of the things that I actually do not do. But one of the important, interesting thing about tree-based method is that it requires a bit less of data wrangling. For example, you don't need to normalize your data scale, so because usually tree-based model is scale invariant. You don't have to shift your data in some way. So in that sense, tree-based model are easier to use, and it requires less feature engineering. Does not mean that you do not have to do feature engineering. You still need to do a bit of cleaning your data and do some more smarter way of cleaning your features.
You talked about imputation, it does automatically, but is there a way to actually control, if, let's say the column has like 50% of the data missing, so what do you do in that case? Because the imputation may not be the best case scenario.
If the data is actually have the same distribution in terms of test and training data, I would say directly using the way that we do here is still the best way to do. Unless your data set is kind of differently distributed from your training and test. Then maybe we want to think about more smarter way of handling missing data.
So how do you avoid doing imputation and XGBoost?
The thing is that basically what we do is we automatically learn how to impute. That's the basic idea. So we learn the best structure to handle the missing directions. So if you have like 50% of missing data, actually that's where this approach actually shines over directly doing manual imputation, because the user's guess is not the best approach. Yes?
Can you talk in detail on how XGBoost does feature importances?
Feature what?
How it does the feature importances.
Feature importance. Okay. Usually, on some tree ensemble model, the feature importance is basically how many times a feature occurs on a split. That's one way of measuring feature importance. There are other ways like measuring what is the gain that you can get by that split, and I think this is also an available feature, but we will check out. Yeah. Yes.
I noticed you're using the web text classification that's set on there. What is that like? Is that like LBA or something? Or how does that work with XGBoost?
You mean web text
I
classification?
saw that listed as one of the things.
Oh, I see. So all this comes from one use case of table winning solutions. So if you go to XGBoost, there's a resource page about winning solutions. If it's not there, it's likely to be on a table winning blog. So you can find out more details about how to do text classification. Yes.
Like one of the most clever things that you guys came up with for XGBoost is approximate weighted quantile algorithm, the theoretical guarantee.
Yes.
I'm actually really curious, where do you see that appearing in the near future in terms of helping other machine learning algorithms?
The quantile thing, I would say that quantile thing is very useful in the sense that not only it can help you to build better trees, actually it can use, for example, you can use it to build approximate histogram, to approximate our data set. I have harder time to imagine how it can be used in other machine learning algorithms yet. Because tree-based algorithm is kind of quite special in the sense that you want to find those approximate quantiles.
Is there a special thing you want to do if you want to apply this to classification problem versus regression problem or a numerical prediction problem?
Usually that's the only thing you need to change is the objective function.
Yeah, so then on that point, how do you choose the object function? Is there
For example, if you do classification problems, if it's binary, usually what you do is you use logic regression. If you use regression problems, depends on whether, if it's something like it's between 0 and 1, you still want to do logic regression. For example, you want to regress the click-through rate of using. But if it's beyond 0 and 1, there are two ways. You can do rescaling, rescale that back to 0 and 1, or you can directly do linear regression. Those are the ways.
Yeah. One last thing about this is that for a certain scenario, like for extremely rare cases, algorithm like SGD could break down because of the numeric issues. Does the XGBoost handle this gracefully, or more gracefully?
You mean the imbalanced data set?
Yeah, imbalanced data set.
So there's the detailed guide on how we can handle it. There are two ways you can handle it. The first way is that if you don't care about prediction probability, so for example, you want to predict click-through rate, but you only care about the rank of the prediction. What you can do is you can rebalance the data set, because actually we support weighted prediction, weighted training, so that you can assign higher weight to a smaller.
Just like weighted distance
Yeah.
where you can assign a weight column.
Yes, and there's another way that actually we can use to. This is not only an everything issue. So we have a norm that you can turn so that it's more stable. When you directly do regression, if you care about prediction of probability. So yes, I wouldn't say it's a problem of the tree-based method.
Regarding missing data, is there any assumption as to the independence of the missing data, or
There's no assumption in terms of distribution of missing data. There's indeed an assumption in a sense that we assume that the missing data presented in the prediction or test data set is in the same manner as the missing data presented in your training data set. I would say that's the only assumption. Yes.
During the training phase, what are the conditions under which it stops splitting further? Like when does it decide that, okay, this is the leaf node?
Usually what it does is that will continue split until maximum depth. Then it will start pruning back. So that it will prune the useless node that does not give you like gains of a certain threshold.
Can you pass on some parameters that say that if you have X number of instances in the leaf node, that's okay?
Yes, there's a parameter that specifically does that.
So you talked about sparse aware algorithm. So what exactly is like sparse aware?
The fact is that the training complexity of the algorithm is linear to the number of non-missing entries in the matrix. So assuming that your matrix is extremely sparse, for example, if only 1% of the entries in your matrix is 1, the rest of them are not presented, it means that the sparse aware algorithm can get you 100 times faster than the normal method.
Yeah, but how does this XGBoost handle it?
That's the implementation detail. You talk about implementation detail. Okay. So I think it's written in the paper. It's harder to directly explain it by a few sentences, but yes. By interest, you can read the paper.
Do you have some benchmarks for like the performance related to the depth of the tree compared to other libraries, like say scikit-learn or something?
Yes, basically in a single, so I think we have the comparisons with scikit-learn in the very beginning. Yes, okay. So this is scikit-learn, and this is, I think, this is actually with one thread. So currently scikit-learn provides a single thread chain. So in a single thread version, XGBoost will run 4 times faster than scikit-learn's implementation. And you can utilize multiple cores, which means you can easily get more than 10 times faster than scikit-learn's implementation.
But same cannot be said about the depth of trees because the splitting
With the same criteria.
But in scikit-learn, you can assign jobs and jobs. Is that a fair comparison you were wanting to benchmark?
What do you mean by jobs?
So in the scikit-learn, for example, gradient boosting tree
Yes.
function, you can assign input and hyperparameters, and you can also assign n jobs equals to n. So it automatically spin out to n cores.
Oh, I see. I don't know that actually they have a recent update of the multiple core implementation, but it would be interesting to compare actually. For this is more like comparing the C. So if you want to only compare the single core implementations, this is single core implementation of scikit-learn, and this is single core implementation of XGBoost. So I would say that's a fair comparison.
There was a pretty recent blog post about hyperparameter tuning for XGBoost. Did you come across that, or are you aware of it? It was an analytics mid-high.
Yeah, I think I've looked at the blog post. Yeah.
Useful? I mean,
I think it could be useful, yeah. So usually, I think we also have some note on how to tune parameters, and if you are interested, usually actually, if you are really interested in the thing, normally just use the default parameter as a start, because although there are a lot of knobs that you can tune, usually use the default parameter already give you a very good start point. But afterwards, try to tune a few parameters using cross-validation is quite helpful. Yeah.
And then also, I know from memory serves, it's a little tricky to install XGBoost on Windows.
Okay. So if you follow the instruction clearly, I think it's okay. Yeah. So the thing is that so on Windows the problem is that we need a compiler on that supports OpenMP, and there's an issue on Bash difference between Windows and Linux. So if there's ever a problem, it's highly likely to use a long version of Bash. We used to have a Virtual Studio. Virtual Studio version that's kind of easier for some people. Actually, we are looking to bring that back. So it's like we want to make it as a CMake version in the Windows. That's not yet brought back, but I think it's a work in progress for the Python users. Yeah. But I think for most of the people, there are a few troubleshooting blog posts on Windows that can help you install the thing without problem. If you are using R, I think it's not a problem because R only have one build system, and that build system works very well. Okay, so one more trick that actually if you want to ever install like XGBoost on XGBoost Python on Windows is that you try to go and grab R's build system for Windows. So R have a build system called RTools that actually used to build the R library for most Windows applications. And if you install RTools, and usually all the things you need from RTools can help you to build XGBoost Windows version without problem. So there are a few people mentioned about scikit-learn. So what I want to mention is that XGBoost is fully compatible with scikit-learn in the sense that it exposes a scikit-learn interface that can work with any of the things that you can use in scikit-learn. So It's just like a clean plugin, but better.
Is the prediction latency comparable to a random forest? Is it correlated with the number of trees you have?
I would say GBM usually have less number of trees if you want to gain the same accuracy. In that sense, the prediction latency will be even lower. And since you are talking about prediction latency, there are two things that you want to consider. The first thing is that the total prediction speed that you have on the data set. So if you can afford batch prediction, for example, you get an entire data set, you do a scoring in a batch fashion, that's fine. And usually that's already very well supported in XGBoost. Another thing that people care about is real-time prediction, that you care about latency. If you want to get a predictor and you want to predict directly. On that end, it's not working very well because I would say it's working okay, but not optimized to the end because of the calling latency between the Python and C++. Because every time for one instance you want to call that prediction. And that's recent progress that we are looking at trying to build a prediction API for XGBoost so that you can do real-time scoring even faster. So in general, I would say if you care about random forest, try tree boosting because usually tree boosting gives you fewer trees. If you like to turn the knobs, it's likely to also give you better performance. And because you have fewer trees, your latency is likely going down instead of up.
So I have one last sort of a different question for you, I guess, more about your impact and how does it feel to create this open source project and see everyone winning all these competitions? Do you feel like, oh, I shouldn't have given it away for free?
I think it feels great. Yes, people, for example, people always ask me how to tune XGBoost. Actually, I would say the experts in Scalable are actually using the tool better than what I can do. But I think one of the rewarding things is that people contribute back, and that's one of the important things. In the sense that if you don't open source it, others will build another library that's open source. So, and if we can integrate well with the existing ecosystem, it's a great thing that we can see more advantages by collaborating and instead of just building something online.
You mentioned Julia before. Can you give me your general comments on the interface to Julia and your general thoughts on how that might improve some of your numbers over the long term, vis-a-vis Python or R?
There's already a Julia package of XGBoost available. In the sense that it wouldn't improve speed in any sense, in the sense that all the libraries share the same backend library. But since there's no existing tree boosting libraries available in Julia yet, I would say it's still the best option that you can get in Julia. But there are a few interesting packages in Julia that actually can help. That are actually helpful. For example,
that's what I'm after.
Yeah, for example, in there's automatic differential library, which allows you to define an objective function without defining a gradient. So I guess that's one of the things in Julia that they can offer you and gives you more interesting results.
All right, thank you. Let's thank Tianqi again for coming to LA, and let's thank Red Bull for hosting us. Awesome venue. Now we can head up for more party.
Please take your drinks with you. There's bins here and along the way. And yeah, please get some more drinks. And
So in a sense, that gradient boosting is a more powerful way to learn those tree ensemble models. Okay. So there are a lot of algorithms to learn tree ensembles. Here are a few of them. Actually, most of the algorithms you can find that these algorithms are invented in the 90s. And actually, all the algorithms that I mentioned in the beginning, like recent hype of deep learning and neural networks, also come from 90s. So if you want to find something that's useful, it's likely that it have been already invented in the 90s. The difference is that we have more data, and we need more powerful tools to fully utilize all this information to get us a good predictor. So what XGBoost does is actually sits on a variant of original version of gradient boosting machine that try to incorporate additional regularization term, which I will explain later. And it really helps us to get a better prediction in many cases. So there are challenges and advantages for using tree-based models. I've mentioned a few already, actually, in the first part of the talk. Tree-based models are usually highly accurate because they can combine all those evidence together. And it's very easy to use compared to other models like linear model or neural network, in the sense that it's invariant to the input scale. So usually if you use other type of models, you need to rescale your input in some nice way so that they don't blow up your training. In tree-based models, it's highly likely that you can directly take your data from a database and throw that into a model and will work out of the box. So it also is easy to interpret in the sense that you can use various tools to inspect what's going on in a learning model. However, there are still a few challenges in a tree-based model. In a sense, the first challenge is that because this model is so powerful, we still need ways to control overfitting. In a sense that we can generalize our prediction well on a test set. The second challenge is that we are getting more and more data, so we really need to build scalable solutions to solve this type of averages. So what is XGBoost? In short, so I've listed a list of features about what XGBoost is, but in short, it's just a powerful system that does one thing very well, in a sense that it's a much faster tool to learning better models. So first of all, in this part of the talk, what I will do is I will tell you what does XGBoost learn, in a sense that to elaborate on what is the better model, what's the better model part mean. Then I will elaborate a bit more on what XGBoost can do for you, in a sense of how it can scalably train all your possible data and the other features that may of interest in doing data science. Okay. So this part of the talk will contain a bit of more mathematical derivations. However, I will only assume basic level of calculus, so hopefully we can follow derivations. I will pause a bit on the crucial part, but trust me, if you pay a bit careful attention, you should be able to derive the general gradient boosting algorithm from scratch. And I think this is a worthwhile thing to do, so that you can all understand what's going on in behind. Okay. So machine learning 101. So there are several elements of supervised machine learning that you need to care about. These are all the key concepts that you want to care about. The first key concept is about model. So a model means that given your input data, say the age, gender, or demographic information of users, how you can make predictions given this information. For example, a very simple model you can use is a linear regression model that basically take a linear combination of all those features and generate your prediction. A second thing about this type of thing is about parameters in the model. So in the linear models, what you will have is you will have a set of vectors that represents the weights you will associate to age, gender, or each of the features. Finally, there's one important thing that helps you to learn those models given the data set you have. This is called objective function. What objective function does is that given the training model, it measures how good the parameter is, so that you can, what you will do is that in the searching algorithm, you will search for the best parameter that fits the objective function. And if you think about objective function, it usually contains of two parts. The first part is about training loss. That's easy to understand. If you want to fit a linear model, it's more likely you want your prediction to be very close, at least on the training data, to be very close on the already provided label. Training loss basically measures how well you can do on the data set you have on your hand. The second term, which is usually actually ignored by many of the beginners of machine learning, is called regularization term. In the sense that it's not enough to only fit well on your training data, because eventually you want to make predictions on your data that you haven't already seen. So you want to be careful to regularize the model such that this model is simple enough so that you can make reasonable future generations. We'll have more examples on this later. So if we put the tree ensemble learning into this context, we can find that it maps nicely into a concept of supervised learning. So if you think about tree ensemble learnings, the model of the tree ensemble is actually a class of regression trees. So say we want an ensemble of k trees. It's a class of k functions, but don't be afraid about the function space. It's just some notations about k decision trees. We're imagining them. And the objective function we use is exactly follows the general supervised learning principle in a sense that we can define a training objective function that measures how well we do on the training data. It can be arbitrary objective function, which means that you can, usually if you look up from the existing literature, you can find objective functions for learning to react.
Red Bull for hosting us, and Brian. This is an awesome venue. So before I introduce the speaker, I also would like to thank Adam and EA for sponsoring Tianqi's trip to LA. So let's thank EA. And Adam is going to tell us a few words about EA.
So just a show of hands, how many of you guys have played an EA game? Alright, this is my kind of crowd. Alright, so if you play EA games and you like video games, we're hiring data scientists at all levels. We have multiple offices around the globe, and we also encourage people who like to travel. So we have offices in LA, we have San Francisco, Seattle, Texas. If you like to stay in LA, we have a couple hundred people here, good data science team. We're part of the larger global analytics team, so we work cross-functionally across the globe, and we work on all of the games across EA, console, mobile. We're primarily focused on the top titles, Madden, Star Wars, FIFA, etc. And we love people who have experience with XGBoost, deep learning, people who like to use machine learning in production, as we do, or people who are really excited about using machine learning to encourage players to have good experiences in the game and personalize how they interact with the game, sending players the right message at the right time, giving them help as they go through the fatui if they're having trouble drifting around corners. We can use machine learning to identify the right way to recommend, hey, remember to press A at this time, things like that. So we're also using it for things like smarter AI, for dynamic push notifications on your mobile phones, and all sorts of new types of applications we're exploring. Doing a lot of exciting things over at EA. Feel free to check out our careers webpage, careers.ea.com, or reach out to me. My email is ahusein, or Adam Hussein, at ea.com. Thanks.
All right, thank you. So, how many of you have used XGBoost before? Wow. How many of you have competed in a casual competition? All right, pretty good. So for the rest of you who have, how many have you heard of XGBoost before the Blitz talk? So even more people. So for those of you who are not very familiar, so XGBoost is one of the most awesome open source machine learning library. It implements gradient boosted machines, which is one of the best, most performing algorithm for supervised learning on many data sets. I use it daily for work, and we are very lucky to have here Tianqi Chen, who is the main author of XGBoost, and who has also received many awards. For example, the John Chambers Award for XGBoost, and also the High Energy Physics meets Machine Learning Award from CERN in Geneva. He's still a PhD student, amazingly, but I think his software beats many of the software that has been done by companies that have put dozens of people working for years. So we're really lucky to have here Tianqi and talk about XGBoost. So let's welcome Tianqi.
So okay, let's get started. Today I'm going to talk about XGBoost scalable tree boosting system. And here's a basic outline. So first I'm going to talk about what is the machine learning model behind. So what is the basic idea, and what can we do to derive all the algorithms in this type of machine learning algorithm. Then I will talk about a bit more about what kind of features we have in XGBoost that can help us to make data science and make machine learning useful in the production. Finally, I will conclude talk with some use cases of real-world impact of XGBoost. So to get started, if you think about machine learning is now everywhere in many of our productions when you talk about data. And however you think about machine learning algorithms, actually there are not too many type of machine learning algorithms that are actually used in production, I would say. There are a few type of machine learning algorithms that are particularly useful. And for example, if you think about large-scale advertising system or other kind of click-through rate prediction system, you will need a good logistic regression or large-scale linear software to solve these type of models. If you think about recommender systems, there's a type of model called factorization model that you want to build all these users' agents and map them into a latent space, and you can use it to do a recommendation. And nowadays, you have heard about this deep learning trend. They can recognize your images and generate audios and do all those magical things that you heard about. And deep learning is yet another type of machine learning algorithm that can be used in production. And today, the major theme of the talk is about tree-based algorithms, actually. So tree-based algorithm is this type of algorithm that's invented in the 90s that are actually not very well recognized. I would say there aren't too many papers about tree-based algorithm recently in academic, but it's still very, very useful in the sense that you can find it in almost all production systems of machine learning. The reason is that tree-based algorithm actually works very well for tabular data. By tabular data, I mean everything that you can pull out from a relational database. And that almost means anything that you can, almost all the things that relate to your production. So as a few examples, you can find that this tree-based data can work on anomaly detection that detects anomaly events. And for example, high-energy physicists use tree-based models to detect potential events in large hydrogen collider so that they can discover novel physics. And it's also used in the click-through prediction or fraud detection to detect fraud. It can also be used to estimate risk or in finance or insurance. So yes, there are a lot of use cases of these tree-based models using tabular data. So what is a tree-based model? I think many of you already heard about decision trees. So today we're going to talk about a bit variant of decision tree that's called classification regression tree. So in here, this is what typical tree-based model looks like in a commercial system. So assume that you want to do a recommendation to see if this person likes computer game or not. So you can recommend product EA to the person, given by the demographic information of the users. So what a tree-based model basically does is that it establishes a few rules to categorize each of the user into each of the categories. And on each of the leaf node, actually, there's a prediction score that basically associates with how likely this group of people is going to like computer games or not. So this simple model has a few interesting perspectives. First of all, you can find that actually it can learn the hybrid of multiple conditions so that it can combine features like age and the gender together. So that you can save you a lot of effort of doing feature engineering in a sense that it can automatically combine some of the features together for you. So usually, if you do tree-based models, a single decision tree, in this type of tree is called regression tree. A single regression tree wasn't enough for solving all the problems. So what people usually resort to is this type of model called tree ensembles. So in tree ensemble, actually, you have multiple trees to make a prediction. So here we have sum of two trees. And to make a prediction of a certain user, what you will do is that you will use the first tree and the second tree to generate two predictions and sum the two predictions together to get your final likelihood score. And this type of model is what model actually generates many of the data of our results in many of the application domains. And there are many ways to learn this type of tree ensemble. For example, one common way is called random forest, which randomly generate independent trees and aggregate them together. Today we are going to talk about different type of algorithm called gradient boosting. That is more powerful in the sense that they will try to learn the trees in a non-independent way. So every iteration, the algorithm will try to add a new tree such that the second tree can complement what the first tree does not.